Okay, we're back, and I wanted to just go through a little bit on constant acceleration, which leads to what a lot of people refer to as the kinematics equations or kinematics relationships. And this is kind of the motion that you study in a first-year class. It's non-calculus based. You're just kind of running numbers through some set formulas that connect acceleration, initial and final velocities, times, and distances that you travel. So there's a good reason for studying this, because a lot of motions, for example, just dropping something moving through the air, free fall, the acceleration of gravity is a very well-known constant. Technically, it's not constant. Gravity changes with height, but for everyday practical purposes, it's around 9.8 meters per second squared. A lot of people around that and just use 10 for the acceleration of gravity. Or if you have a car at a stoplight and it starts to accelerate, we can approximate that as being a constant acceleration. Runners, running races and things like that. Let's use a lot. The first one to really start to figure out these relationships was Galileo, just having things roll down hills. And on a hill, as long as you have a constant incline, would be a constant acceleration as well. And so these are the very well-known set of equations. You can figure out how far you travel in a certain amount of time if you know your acceleration value. You can figure out speeds. You can figure out both initial and final speeds, things like that. And these tend to work best just by kind of playing with them, getting some practice problems in to see how all these things get related to each other. So let's do two quick examples. I'm not going to be too worried about the final answers. You can work them out. The setup is more important because one thing that becomes an issue with these equations is you have to pay attention, be aware of direction, positive directions and negative directions. Some of these terms will have plus signs, others will have negative signs. And free fall is a really good example of this. Okay, so let's assume that you're just going to drop something heavy, a big rock or bowling ball or something, and we know it's going to fall 50 meters to the ground. Let's use 10 for gravity, just to keep the number simple. And let's say by the time it falls and hits the ground, how fast is it going and how long did it take? How many seconds did it take to fall at 50 meters? Those are the two problems. When you have these, and we know it's constant acceleration, we can kind of pick and choose among the three equations which one will make your life the easiest. And so let's say, for example, if we wanted to find the time it takes to fall, well, we know the distance. That kind of implies, well, maybe the distance equation would be the thing to use. And let's just see what happens if we run the numbers here. So let's look at these terms. To get the signs right, up is the positive y direction and down is the negative y direction. So usually, but for me at least, I tend to choose the lowest point in the problem as your zero position. So maybe this might be like my zero height down at the ground. Okay, and so if we think of that distance equation, your final position is the zero. You end up on the ground. You have 1/2. And now for gravity, for the acceleration, we know it has a numerical value of 10, but gravity is always down. Okay? The acceleration of gravity is always down. This will always be a negative number, okay? The negative y direction. Now we're trying to find out the time. That's what we're trying to solve for. If you're dropping this from rest, the initial speed is 0. Okay, so that middle term is 0. And then we have the plus the initial height, which is 50 meters. Okay. And so we can go ahead, we can find the time just from this. If this first term here is going to be -5t squared plus 50 is equal to 0. And if we solve for the time, again, I'll let you do a step of algebra, but it's going to be the square root of 10. And that'll have units of seconds. It's a little over 3 seconds to fall 50 meters. What if we wanted to find the final speed? Well, if we look at our equations, this middle one here, the velocity equation, the initial velocity is 0. The acceleration is gravity, so -10. And we just figured out the time it takes to fall. We can just kind of plug and chug into that to figure out what the final speed is when you hit the ground. Okay, 0 is the initial speed. The acceleration is -10. The time that we just figured out is the square root of 10. Now notice you get a negative number, -10 root 10. This have units of meters per second since it's your actual speed there. What's that minus sign? Well, the minus sign tells you the direction it's moving. Okay, it's moving downwards right before it hits the ground, and it's moving that fast, a little over 30 meters per second. Okay. So moral of the story is be careful of signs. Think what's your positive direction, what's your negative direction, and which direction do each of these different variables point, the acceleration and your velocities. Okay. Now, second example is a race. And you can imagine that at a starting line, you have a truck and a car. And let's say that trucks are bigger and heavier and they tend not to accelerate as fast as cars. So it has a slower acceleration than the car will. So let's say that you give the truck a head start, okay, a 2-second head start. And we want to know how many seconds does it take before the car catches the truck? Okay, so some distance away, that the two will be tied. Okay, the car will caught up to the truck. Okay, so let's take the truck first and just figure out, well, in 2 seconds, where is it going to be? And how far ahead of the car will it be, and how fast is it already going by the time the car can start? Okay, so for the truck, we can just figure out, well, how far does it travel? And use that distance equation. So 1/2 times the acceleration. Now we know the time. The time is 2 seconds. And that has to be squared. We'll assume that each of these are starting at rest, and that they're both starting at 0 over here. Okay, 0 position. So the other two terms in this equation we don't care about because those are 0. And so it looks like it'll be 4 meters from the starting line. Okay. So that's where the truck is when the car is able to start. And that's the head start. Let's also figure out how fast the truck is going at that moment, because it'll be moving now when the car is starting from rest. So we can use that middle velocity equation. Again, the initial speed was 0. We know the acceleration, and we know the time. So it's moving 4 meters per second when the car starts. How do you do this then? Because what's going to be the same for the car and the truck from this moment, now that the truck has the head start? Well, in some fixed amount of time, the truck has a shorter distance to travel compared to the car. Okay, now, so the car has to travel the full distance in the same amount of time that the truck has to travel a shorter distance. Okay, the final position minus the 4 meters that it now has as a head start. So these each are going to take the same amount of time to travel the two different distances. So it looks like time is the kind of the variable that has to be the same for these two in order for the car to catch up with the truck. Once we know what the head start is, like we just did. Okay, so think about this picture, and I'm going to use the position equation here. Look how I set this up. Let me do it in red. Okay, so for the car has to travel the full distance. It has X final. 1/2 Now the acceleration of the car is 4. We don't know how long it's going to take to travel that distance. It starts off at rest, and it starts off at 0 position. Okay, so that's all we have for the car as far as that distance travels. For the truck, okay, now the distance it has to travel in the same amount of time is whatever that final total distance is minus the 4-meter head start that it had. And we know its acceleration is 2. We're trying to figure out the time it's going to take for the car to catch up to it. But now it also has an initial speed when the car is first starting. And we just figured out the initial speed is 4 multiplied by whatever that time is. Okay. Think about how I'm setting this up. So we have a little system here. With the car's expression, x final is 2t squared. I'm going to take that, I'm going to substitute it into the truck equation over here for x final. Over here, we can simplify it a little bit. 1/2 times 2 is 1. We have 4t. It looks like we're going to have a quadratic equation. That happens a lot with constant acceleration because of this time squared term that we have in the distance equation. So if I subtract t squared and bring it over to the left-hand side, 2t squared minus t squared is t squared. I have to move the 4t over there, so minus 4t minus the 4, and that's going to be equal to 0. And we can set up a quadratic equation for this and solve for the time. Now, a lot of you might just have this already pre-programmed in the calculator. If you do it from scratch, it's negative b plus or minus the square root of b squared, so it's going to be 4 squared, plus 4ac. That's all over 2a, which would just give us 2. And in the end, you get something like 8 root 2. We want the positive solution always for time. So we can actually figure out the time. I'm not going to worry about what number that is. But we do that by solving the system. If you have these more complicated types of situations using constant acceleration, I always suggest drawing the picture out if you're not provided one, and really kind of pick and choose these 3 kinematics equations that fit your needs based on what's given and what you're trying to find. So you can do that for races, anything with constant acceleration, anything with gravity, as long as there's no air friction. And this set of equations turns out to be a pretty powerful thing for lots of different kinds of everyday problems. So I hope this helps. And until next time, we'll see you later.